opened up and answer any questions that you may have. I think also by I am not muted. Can you, I'm sure you can hear me now. Now the question is whether I can hear you. Okay, one of you talk to me. I want to know if I can hear you because that's what happened in the lecture.
I see Jaffa.
I can't hear anyone. When it's talking, I can't hear.
Can you,
So
can you not hear like
hold
any?
on a second here. I know it's my AirPods that got messed up somehow. Let me disconnect and reconnect. Yeah, if I'm not on the AirPods, you can hear me, but I don't think I can hear anybody. That's just a problem. Yeah, it won't be on my AirPods. Can someone talk to me? So I want to make sure I can hear you. Kelsey, say something.
Something.
Yes, okay, I heard it. Good, because that's what happened in the lecture. I'm so sorry. I don't know, some weird connection here. But what I wanted to point out was the functional group carbon is important. And if the functional group carbon is connected to one other carbon, it's primary alcohol, two other carbons, secondary, and then of course three is tertiary. The reason this kind of classification is really important is not all of them undergo the same reaction. And even if they do, the time it takes to react is different. And we can use that to distinguish the three types of alcohols. Apart from these three types of alcohols, you have a fourth type, which are called the phenols. And it's something that you have studied, and not too much about it, but just the fact that if a hydroxyl group is connected to the benzene ring, it's called a phenol. So if you look at the functional group carbon, that's the one that is. This is the functional group carbon. And that carbon is actually connected to two other carbons, but it's never considered as a secondary alcohol. It is just considered as a phenol. Okay. I want to draw another contrasting structure here. So if I draw the same benzene ring, then I draw a CH2 and then draw a hydroxyl. Now this carbon is my functional group carbon because that's the one that's connected to hydroxyl and that's connected to one other carbon. Okay. Now this is considered a primary alcohol. The classification is important, not just really for nomenclature, that's kind of dull and boring, but it's really for the reactions, because the phenols show very unique reactions because the functional group carbon is an sp2 hybridized carbon. When the functional group carbon is sp3 hybridized, those are your primary, secondary, and tertiary alcohols. So if you look at the primary, secondary, and tertiary alcohols, all functional group carbons are sp3 hybridized. So as soon as it becomes sp2 hybridized and it's part of a ring, the chemistry does change. So phenol shows some of the reactions of alcohols, but not all of them. Because of the uniqueness of the structure of a phenol, it has its own characterization test. So when we come to the test, I'll point that out. So we're going to first start with the steric ammonium nitrate test. Now, steric ammonium nitrate is a yellow solid. You can make a solution of it in water, and it's yellow, but it's a clear solution. If you add an alcohol to it, it's going to give you a reddish color, okay? Now, all alcohols will give a positive test, whether it's primary, secondary, or tertiary. This is not for phenols. So when I say alcohols, I mean positive test for primary, secondary, and tertiary alcohols. And the positive test is a clear yellow solution giving you a reddish color. Now let's take a look at the ceric ammonium nitrate, the structure right here. This is the one I'm referring to. I want you to give me the oxidation state of cerium. So you have cerium right there. I want you to look at that structure and tell me what the oxidation state is in this compound for cerium. So nitrate is -1. You got 6 negative charges. You have a residual 2 negative charges there, which is balanced with ammonium, which is 2+. So will that help you determine what the oxidation state is for cerium? It's a transition element that can take multiple states. It's got to be 4, right? Has to be 4+, because that's how you get the 2-. So cerium is 4+, and one of the nitrates is removed and it's replaced by an alcohol. Okay. Because it's a transition metal, it can bind to more than one alcohol, and both the top reaction and the bottom reaction are correct. The bottom reaction is from lab flow. The top reaction is what we have used in our classes, and that's fine too. You can use whichever one. This one just shows 2 alcohols. So for every alcohol, you will remove a nitrate and you'll get the ammonium nitrate. So this one is nice because it's a fully balanced equation. So that's the chemistry behind it. You form a different complex. The nitrates are substituted by the alcohols, and these kind of groups are referred to as ligands. So that's transition metal chemistry. I don't know how much of that you studied in Gen Chem. And once the ligands change, the colors change typically. So the clear yellow becomes reddish. It's a positive test for all types of alcohols. Now, any questions there? Please let me know. Now, the ferric chloride test is a test specifically for phenols. So this is your phenol. So a positive test, the ferric chloride is a yellow, again, it's a clear yellow solution, which is made in water. So the yellow solution can turn into a deep red to purple. It's an extremely sensitive test, which means even trace amounts of phenol will give you a deep color. Okay, so the purple can become really deep, and that's when it takes on a deep red color. Now it's again a complex form between this alcohol and ferric chloride. Again, I want you to tell me what the oxidation state is for iron. Each chloride is -1, so iron is 3, right? Then we got phenol. Iron is a Lewis acid because it's got only 6 electrons. It needs 8. So this is going to be a fast reaction. Chloride's going to leave. So you get FeCl, hydroxyl group, the benzene ring. Then hydrogen and Cl combine to become HCl. So this is what imparts the color. So this reaction is a very simple acid-base reaction, occurs extremely fast to give you that color. It's a positive test for ferric chloride. It is a test used by Bayer, the German company, for making aspirin. So when we make aspirin in the lab, we want to make sure it's not contaminated with any phenolic compound, because these are acidic. That's why one of the reasons you cannot use aspirin beyond the shelf life, because some of the aspirin degrades into salicylic acid, which contains the phenol, and that's what causes severe stomach burns. So whether aspirin is 100% aspirin or is contaminated with any phenolic compounds is determined in the pharmaceutical industries using the ferric chloride test, simply because it's a very sensitive test. Even trace amounts will show a deep purple coloration that you cannot miss. Any questions there? So that's the test that's used for classifying a phenol. Next comes the chromic acid test, which we have studied, and it's called the Jones oxidation or the Jones test. Now, what is shown here on the top is a primary alcohol, which gives a positive test. Secondary alcohols also give positive tests. Tertiary alcohols do not react. So it's a negative test with Jones reagent for the tertiary alcohols, but the other two react very well. Now, in both cases, what we will use is a variety of chromium reagents. You can use potassium dichromate and sulfuric acid. You can use sodium dichromate. You can also use chromic acid. With water. So any of these, chromium is going to be in the 6 oxidation state, and eventually it's an oxidizing agent which gets reduced. So it gets reduced to the +3 oxidation state. The most important thing to remember is the color change, because these are visual tests. See, any of these chromium reagents, the positive test is all the chromium reagents are a deep orange color, and it'll become a dirty green color. The dirty green color indicates the chromium +6 has become chromium +3. So you get a positive test for secondary alcohols, positive test for primary alcohols, tertiary alcohols do not react. So what happens with the primary alcohol is first gets oxidized to aldehyde. Aldehydes then become carboxylic acid, which is the final product. The secondary alcohols, no matter what you use, mild or strong oxidizing agent, your final product is a ketone. So something that we studied in the class extensively. So it's the color change that's important for us today. The next text is new information. So we'll spend some time on it and learn this. This is called the iodoform test. Iodoform test is very specific for one kind of alcohol, which are called the methyl alcohols. In other words, if you have a methyl group attached to the functional group carbon, it's going to be a positive test. It's a positive test for alcohols if a methyl group is attached to the functional group carbon. So right here is your functional group carbon, and you can see a methyl group attached. We need that methyl group to get this positive test for iodoform. The positive test is you get a yellow precipitate. This yellow precipitate is iodoform, and this is your positive test. Okay. So what happens is iodine is used in this reaction for the iodoform test. Iodine is a mild oxidizing agent. So you can see how this is a secondary alcohol that you're taking here becomes a ketone. No matter what you add to the secondary alcohol, whether it is strong or weak, it's always going to become a ketone. Okay, so it has become a ketone here. Now, this ketone has a methyl group. Remember, this methyl group is really important for us. Therefore, this ketone it's got a special name. It's called a methyl ketone. Nothing too fancy. It's the methyl ketone. So that is the oxidation part. I want to show you how the iodoform is formed now. So let's take a look at that methyl ketone. So I'm going to take CH3, C double bond O, then just write an R group here. Then I'm going to treat it with iodine. You still got iodine. And remember, this reaction takes place in very strong sodium hydroxide medium. That means you need strong alkaline medium. pH has to be really high. So what I'm going to do is a little modification. I'm going to write this as CH2 and hydrogen. Sodium hydroxide comes in, grabs a proton. This is an acid-base reaction, leaves the lone pair, the sigma bond as a lone pair on top of the carbon. So what we're going to get here is CH2, lone pair, negative charge, C double bond O, R. Now iodine comes in, okay? So what's going to happen now is this is going to attack the iodine. This is going to leave. So this is going to give us, this is all new chemistry. We haven't studied it yet because it comes in aldehydes and ketones chapter. So you have it iodinated. Now this reaction can keep continuing. You still got, if you realize you still have your 2 hydrogens here, right? You can keep continuing. What I mean by that is another hydroxide can come in, grab the proton, and again you can get an iodine. So you will exhaustively substitute all 3 hydrogens with iodine and get C double bond O R. So there will be an exhaustive iodination that takes place at the carbon. What that means is every hydrogen is successively substituted by the iodine atom. Keep in mind this is strong excess sodium hydroxide. You've got plenty of sodium hydroxide. So what's going to happen is the sodium hydroxide now attacks this carbon. This double bond becomes, minus charge, moving towards the oxygen. So you get CO minus hydroxyl, and R. Now this comes back down, and this is a good leaving group, so it leaves. So you get Ci3 minus plus C double bond O, or hydroxyl. Now the I3 minus is going to grab a proton. Okay, if you want to draw an arrow, you can. You can have it grab a proton, or you really don't have to show those proton movements. But this becomes CHI3. This is your yellow solid. This is the iodoform. And then, of course, your side product is going to look like this. Yes. So I'll bring the whole thing on the screen here. This entire thing is called the iodoform reaction. We do study this, and it's an important reaction. We'll give you a nice crystalline yellow precipitate. Then you know you have an alcohol, but not just that. You know you have a methyl group right next to the alcohol. So let me know if you have any questions here with any of these arrows. So I numbered them in sequence, so hopefully that helps out. Okay, our last test is the Lucas test, and this is a distinguishing test between the primary, secondary, and tertiary alcohols. So Lucas test is basically taking an alcohol, zinc chloride and HCl. What I want you to know to understand this test is that it is an SN1 reaction. So if it's an SN1 reaction, that means it is 2 steps. It goes through a carbocation intermediate. Once we get to a carbocation, we should remember the stabilities. Tertiary, more stable than a primary. A tertiary carbocation can only be obtained from a tertiary alcohol, right? Unless there are rearrangements, a primary carbocation typically from a primary alcohols. So what this means is tertiary alcohols will react the fastest, followed by secondary, followed by primary. So this will be the fastest reacting with alcohol under the Lucas test conditions. This one reacts the slowest, which means we're just going to say it does not react because there's a time limit. You don't wait for hours. Now the reaction itself is simply a substitution reaction. So you replace the hydroxyl with the chlorine. So the positive test is, there are 2 kinds of positive tests you can get. One is an oil lake on top of the reaction solution. So what I mean by that is if you have a test tube, you pour all the contents, you shake it, you might get a thin oil floating on the top. That's your product. It's because it's insoluble, it floats on the top. But if you shake it, you'll get a cloudy, suspension or a mixture. What that means is this is just shaken and all of it is mixed. And so a positive test, if you let it sit, you'll see an oil floating on the top. If you just give it a good shake, it'll be a cloudy mixture. And the timing is what's really telling you it's an SN1 reaction. Tertiary alcohols, immediate, because a tertiary carbocation forms right away. Secondary alcohols, a little bit more time. Primary carbocations are extremely unstable, so the reaction will not even occur in a reasonable amount of time. Okay, so that is the Lucas test. So a positive test for tertiary, positive test for secondary takes more time, negative test for primary. Combination of all these tests, one should be able to find out what type of alcohol you have. You still don't come up with the exact name because for which you need spectroscopic techniques, but it still gives you a pretty good idea about the classification of alcohols. Okay, let me know if you have any questions with any of these tests. What I want to do now is I'll wait for your questions. So we are going to go into your lab flow and we are going to start with this first. Okay, I'm always careful with lab flow because anything I select, the first thing it shows up are the grades. So I don't want to do that. And so I got everything open ahead of time. This is a procedure. It explains all the tests in detail. So there is your ceric ammonium nitrate test. You have the ferric chloride test. This is a Jones test. Then we have the iodoform test, and I gave you the mechanism for that. We have the Lucas test, and you do have some information. That's an SN1 mechanism. That's what's really important to remember. And that's the procedure. Now this everybody has. Everyone gets the same unknown. So you're asked to write the unknown code in the lab report, and I'll show you that. You're going to say B. So, and then if you did this unknown in the lab, these are the observations you're going to get. So the observations are already provided to you. Solubility, you're being told that your unknown is not soluble. Ceric ammonium nitrate test, you're told your unknown gives a positive test. That means it's an alcohol. It does not give a positive test with ferric chloride. That means it is not a phenol. Okay, so all of this information is given. You're simply going to write these observations in your lab report. Now we'll go to the lab report. So the unknown code, you're going to write B, right? Solubility test, this is what it is. For the unknown, you'll go to the sample data. It says unknown, insoluble. So you're going to write insoluble. So everything else, you're going to estimate your solubility. Okay, so now for estimating solubility, you want to be careful about it. Let me just jump back to this to show you something and how you're going to predict solubility. This prediction sometimes is hard. You know, it's easy to take these alcohols, put them in the solutions and see, you know, if they react or if they're soluble or not. So when you take an alcohol group, keep in mind, it can hydrogen bond with water. So typically small alcohols will be very soluble in water. A good example is ethanol. As you start increasing this R group, this becomes longer and longer. So if you have really long chains, what happens is you have a hydrophobic part. That is a part that does not like water. That's your alkyl group. And then you have a hydrophilic part. That is your hydroxyl group. However, if the hydrophobic takes over the hydrophilic, then the alcohols are not soluble in water. And a good example are your cooking oils. Those are alcohols and they're not soluble in water. Okay, so you want to be careful as you know, you start predicting solubility here. Keep in mind, as you start increasing the number of carbons, you know, it can become water insoluble. But you're also given another thing saying slightly soluble. So if you're somewhere between a high solubility such as ethanol and insoluble like 1-octanol, I would say is insoluble because you got 8 carbons and you only got 1 hydroxyl group. Somewhere in between, like halfway through butanol, maybe it's sparingly soluble. So you're going to make some guesses there. The ceric nitrates test, ceric ammonium nitrate test, you're going to make a guess for the first two. The unknown, you're going to get it from the sample data that's provided. You're going to do the same for the ferric chloride test, the chromic acid test, the iodoform test, and the Lucas test. And then you're going to describe your unknown based on the test. So when you describe the unknown, you're going to say whether it's an alcohol, phenol, and if it's an alcohol, you want to classify the alcohol as primary, secondary, or tertiary. Okay, so the alcohols that have been provided for you are these. So your unknown is one of these: ethanol, 2-propanol, butanol, 2-pentanol, 2-methyl-2-propanol, 1-octanol. It's one of them. Your sample data is given there. So if you can actually go a step further and say which one of these alcohols it is, that is great, and you can do that. So go ahead and go one step further and also identify the alcohol. So if you're wondering what's the alcohol unknown list, it's one of these. You have the entire list here, ethanol through 1-octanol. Your unknown is one of those. Okay, and all of you have the same unknown. Then comes the post-lab questions. Okay, that's with your lab report. Do you have any questions on how to write the observations or anything at this point? Later, you can always email me or meet me. Is it the same unknown for all the tests? Yes, it is, Olivia. It's the same unknown. It's unknown B for all the tests. And how the unknown reacts with all the tests is provided in the sample data. You have this in lab flow. So if you go to the main lab flow screen, you should be able to find it. So Harry had a question and someone has given him a suggestion. I don't know. It is supposed to be PC and Mac compatible. I'm not sure whether it is Chromebook compatible, but it should also have an app. That's my understanding. The post-lab questions. Let's start with the first question. An alcohol is oxidized by chromic acid but does not react with the Lucas reagent. So I'm just going to explain to you a little bit about this, and then you should be able to answer the other questions on your own. So if an alcohol is oxidized by chromic acid, what that means is I'm just writing some hints here. These are not the complete answers. So if it is oxidized, if it's a positive test with chromic acid, what this means is it's a primary or secondary alcohol. It is definitely not a tertiary alcohol. So if it is a negative test with Lucas reagent, okay, next line. Next, it's I know what it's doing. So negative test with Lucas, then what it means is the one that does not give a positive test with Lucas is a primary alcohol. Because with the Lucas reagent, both the tertiary and the secondary will give you a positive test. The secondary takes some time. So what kind of alcohol is it? It is a primary alcohol, and you want to explain the answer, okay? So similarly, you're going to answer questions 2 and 3. They are not difficult at all. And then if you have any notebook pages, any further explanations, you can upload it here. And that is it for your lab for today. You do not have any relevant Spartan experiments for today because it's only classification of alcohols. When we return next Wednesday, I'll open up the next 4 labs by then, which I'll do later today. It should open up in Canvas, so you'll be able to do your pre-lab, whatnot, and we'll be ready to move on. So we have 2 more experiments, 1 more in alcohols, 1 more in ether and epoxides. And then we'll get into aromatic compounds. By that time, we would have covered enough theory about reactions of aromatics. So I've set up the schedule intentionally like this so that in the lab, we are a little behind the lecture. That way you get a lot of information in the lecture, so the lab becomes a lot easier for you, particularly because you're doing this online. You don't want to be dealing with too much new information. So that's all I have from my side. If you have any questions, lecture or lab, I'm more than happy to answer that now. If not, from my side, I am done. So you guys have a good afternoon.
I was doing wrong.